Okay, so we are going to use our force analysis process to look at an example of a case of equilibrium. And we mentioned what equilibrium was when we started to look at sort of the conceptual ideas of forces. But equilibrium is a state where the net force on an object is equal to zero. We talked about that happening in two different ways. One, static equilibrium, where that net force of zero is resulting from the object not moving. So the object's not moving at all, and there's a net force therefore acting on that object of zero. The other is dynamic equilibrium. We'll do an example problem like that as well in another mini lecture or mini example. And that's when the object's moving at a constant velocity. So it's not changing its motion, but it's moving in a constant manner. So the net force is still zero. It's in equilibrium, but in a dynamic way, moving at a constant velocity. So both are going to be important for us to think about as we do force analysis. And as we look at the forces acting on an object, we want to be able to recognize if we're in a state of equilibrium. That's going to be important. All right, so we're actually going to look at the example out of your book, example 6.1. And the reason I want to do this example and use these examples is because your book does it a little bit differently than the process I outlined in the mini lecture. And I want you to be able to see how they're related. And then use the process in as clear of way as you can as you analyze this material. All right, so example 6.1 reads, your kneecap, your patella, is attached to a tendon to your quadricep muscle. This tendon pulls at a 10-degree angle relative to the femur, the bone of your upper leg. The patella is also attached to your lower leg, the tibia, by a tendon that pulls parallel to the leg. To balance these forces, the lower end of your femur pushes outward on the patella. Bending your knee increases the tension in these tendons, and both have a tension of 60 newtons when the knee is bent at a 70-degree angle between the upper and lower leg. What force does the femur exert on the kneecap in this position? All right, so if we think about that force analysis process that I want you to use, that we went over, the first thing we want to do is identify the object. What is the object that is experiencing the forces? And in this case, it's the kneecap. All right, the next step is to draw a picture. Okay, I'm not very good at drawing in terms of legs and everything, so we're going to sort of wing this one. It says there, here's kind of one bone, and here's another bone, and here's the kneecap. Nice, huh? Yeah. Okay, so we have a couple tendons, one like this, one like that, and then, of course, the head of the femur acting on the kneecap. That's really awful. Okay, so the next thing we're going to do is look at a coordinate system. Now, the suggestion was to use a coordinate system that aligns in the direction of an acceleration. So on our picture, putting the acceleration is helpful. Well, what is the acceleration if it's just sitting there? Nothing. So the acceleration is zero. Now you can do this a lot of different ways, but I really like to look at things in the normal Cartesian way. It's more intuitive to me. So I would make my coordinate system the normal Cartesian system that we're more comfortable with. Then that'll help us identify these forces. All right, which of course leads to the next step, which now you could add a origin. We're not doing motion in this example, so we don't need to do that. But if we were moving the kneecap along, we might identify the origin. Okay, the next thing is the interactions. What forces are acting on the kneecap? Now, typically we'll often say, oh, the force of gravity is acting. In this example, the force of gravity isn't contributing to the forces that the kneecap is actually experiencing. We're really focused on looking at how, the kneecap could be resting on something, it could be acting on something. We're going to just assume in this example that the force of gravity is balanced by a support force, so that the object is not accelerating up or down vertically. We're going to keep it out of our drawing for now because what the causes are might be a little more difficult to assess. All right, so we're just going to, like I said, assume that those two forces are balanced. So let's look at the forces that are described for us. We have the tendon for the femur. So we'll say force 1 is between the kneecap and the femur tendon. And how is that angled? Well, it tells us that that kneecap is angled 10 degrees relative to the femur. So if we make our free body diagram and we identify our coordinate system on that free body diagram, then the tendon, femur tendon, acts 10 degrees with respect to that horizontal. So 10 degrees from that where the kneecap is. Okay, so there's our femur tendon. The next force is going to be that tendon that's going to the tibia. So that's between the kneecap and the tibia tendon. Now in this case, it tells us that the tibia tendon is parallel to the leg. So whatever the angle the leg is at, that's the angle that the tibia tendon is. And it's at 70 degrees. So the angle here is 70 degrees. That angle. So there's our angle for the tendon for the tibia. I made that much too long relative to the femur. All right. Then we have the head of the femur pushing on the tendon, on the kneecap. Now, that means we must have a third force, force 3, between the kneecap and the head of the femur. So we'll just say the femur itself. Okay, so we got to draw that on our free body diagram, but I don't really know how it's pushing. I don't know if it's pushing horizontal or vertical or how it's pushing. So I have to sort of kind of make a guess a little bit, use my intuition. I know this is in a state of equilibrium because nothing is moving. So I know these forces are all going to balance out. So if I have two forces pulling me to the left, I must have a force to the right. So I can probably deduce that my femur is going to be pushing to the right. Now the question is it pushing up and to the right or down and to the right? This one's a little maybe more difficult to intuit. So it's okay if we just put in an angle, we'll call it theta, and the physics should tell us if it's up and to the right or down and to the right. What we determine for that theta should come out in the physics based on the components that are needed to be in equilibrium. So let's use that idea and see if we can develop this magnitude of the force on this number 3, force number 3, and the direction. Okay, free body diagram, interactions, done. Now we're going to separate the forces into horizontal and vertical components. So I like to number them. Force number 1, 2, and 3. Okay, and just because we're not looking at the problem in parallel, let's remember that the kneecap is 60 newtons at 10 degrees. And the tibia, the kneecap and the femur tendon is at 60 newtons at 10 degrees. And the kneecap and the tibia tendon is also at 60 newtons, and it's at that 70 degrees with respect to the negative x-axis. Okay, this 10 degrees is also with respect to the negative x-axis. All right, and we have no idea about that one. I dropped my blue. Hang on a second. Okay, so let's separate our forces and look at how they relate. So we have horizontal. Oh my goodness, I'm all fingers. We have our horizontal forces and our vertical forces. So force number 1. Force number 1 is 60 newtons. This is my 70 degrees with respect to the x-axis. So the horizontal component is adjacent, cosine. So we have 60 times the cosine of 70. That gives us 20.5 newtons. But it's pointing to the left. So I need to remember that this then becomes negative 20.5. 20.5. Okay, what about my vertical? Squeaky. Vertical is the opposite. So 60 times the sine of 70. And that's 56.4. But again, it's pointing down and to the left, so it needs to be negative 56.4. So there's my horizontal and vertical components for force number 1. Force number 2, let me give myself a little bit more room here. Force number 2, I don't know, but if I make my force number 2 relative to the positive x-axis, then I know that my horizontal component is going to be the cosine of my angle. And I know that my vertical component is going to be the sine of my angle. So that's all the information I have for force number 2. All right, well, what about force number 3? Well, force number 3 is 60 newtons at 10 degrees with respect to the negative x-axis. So here's my 10 degrees. The horizontal component is the cosine. So I have 60 times the cosine of 10. And that gives me 58.1 newtons, but I'm pointing to the left, so it's a negative 58.1. My vertical component is opposite the angle, so 60 times the sine of 10, which is 10.4. And I'm pointing up, so it should in fact be positive. All right, so those are separating my 3 forces into their horizontal and vertical components. Now I can sum those forces and apply Newton's second law. Newton's second law tells me that the sum of the forces horizontal is equal to the mass times the acceleration horizontal. Well, in this case, there's no acceleration, so those sums should equal 0. Similarly, the vertical is the sum of the vertical forces times the mass times acceleration vertically. Those should be summing to 0 because there's no change in motion vertically either. So if we add these together, the sum of the forces horizontal is equal to minus 20.5 plus force 2 cosine of theta minus 58.1, and that equals 0. So minus 20.5 minus 58.1 tells me that force 2 times the cosine of theta minus 78.6 equals 0. So F2 cosine of theta equals 78.6. Okay. What about in the vertical direction? Well, in the vertical direction, I have the sum of the forces vertically is equal to minus 56.4 plus force 2 sine of theta plus 10.4. And those all equal 0. So minus 56.4 plus 10.4 gives me 46. I have F2 sine of theta minus 46 is equal to 0. So F2 sine of theta is equal to 46. All right, now how then do I solve for this particular problem? Well, I'm going to have to use a little trigonometry. So I can solve both sides for F2. F2 is equal to 78.6 divided by the cosine of theta. And F2 is also equal to 46. Well, let's put it over there. F2 is also equal to 46 divided by the sine of theta. So I should be able to set these two equal to each other because they're both force F2. So I have 78.6 over the cosine of theta is equal to 46 over the sine of theta. A little algebraic rearranging, if I multiply both sides by sine of theta and divide by 78.6, I end up with sine of theta over the cosine of theta is equal to 46 over 78.6? Well, the sine of theta over the cosine of theta is the tangent. So this is equal to the tangent of theta, which tells me that theta is equal to the inverse tangent of 46 over 78.6. So if I take the inverse tangent of 46 divided by 78.6, I get 30 degrees. So my angle is 30 degrees for this force. I still need to know my magnitude. So now that I have my angle of 30 degrees, I can plug that in. The force 2 is 78.6 over the cosine of 30. And my force 2, 78.6, divided by the cosine of 30 gives me 90.6 newtons. So in your book, we have a little bit of rounding differences. So your book did not round at all through the process. I did. So we're going to have a little bit of variability in our final answer because of that. So 91, your book gives me 92, angle is the same. So I'm comfortable with this process and what we did. I personally like to get those numbers in right away. Your book, of course, left it all as sines and cosines. So again, you can do your preference. The physics is what's important. The rounding and the early rounding, I rounded a little early and a little much. It's certainly going to change our answer, our numerical answer by a little bit, but not in the grand scheme of things in terms of the physics. So the important part here is following that process. Recognizing that we're in a state of equilibrium, so the sum of the forces ends up being 0, and then using that to solve the problem. But really identifying the object, identifying our picture and our acceleration, doing the interactions, free body diagram, separating those two forces into horizontal and vertical components, applying Newton's second law, solving, and a little bit of algebraic manipulation and trigonometry to get our answer. All right, good job.